See, they're unedited videos, so they're just
Oh, that's the guy I met earlier. Apparently, he's an art director and Ruby needs his feedback on her Chocobo illustration. And what better way to get feedback than from the man who created Mini Chocobo himself almost 30 years ago? Has Chocobo changed over the years?
だんだんやっぱり変わりますね。一番初めからすると少しだけこうスマートになったかもしれない。
I guess I can see that.
これを真ん中でこう切ってもらって。
Now, they're working on a Chocobo record soundtrack cover from the Final Fantasy series. He says he needs to illustrate a 2-page spread since the cover encases 2 records.
最終的にはこうお祭りを眺めてるチョコボの家族というか仲間たちっていうのでまとめたんですけども、まずいろんなラフを書いてチョコボが走り回ってるやつだったりとか、こう仲間となんかこう冒険に行くところだったりとかいろいろ考えておいたんですけど、このアイデアを決めるまでがかかりましたね。
It took him about a month to draw this. The approval process must have been insane. How's the Final Fantasy illustration going?
朝よりはちょっと進みました。顔周りが少し綺麗になったかなと。
So are you done?
これからもうお家に帰ります。
Yay, finally done. She says that she could probably work a little longer, but tonight she has plans to play an online game with her friends, so she decided to call it a day. When she plays online, she usually has a drink or two with a light meal while chatting with friends. So before the game starts, she prepares her dinner. Do you have any specialties?
一番得意な料理。でもお味噌汁かな。お味噌汁。
Oh, I guess she's making a peach mozzarella dish. Looks good. So, that's all you're eating tonight?
ご飯今日はお酒入るんでこれだけ。今日野菜ゼロです。
Oh, it seems like her friends are online now.
なんかすごい疑います。
Oh, you stopped talking to them now?
なんかもうゲームのルールで今は会話をしちゃいけないんですよ。
Huh, that's fun, I guess. So it looks like Ruby is going to be playing this game until 10 with her friends, enjoying, and then after that, probably take a bath, and then probably go to sleep at 12. That's pretty much a day in the life of a Japanese game illustrator. If you guys like this video, definitely help me out and hit that like button. If you guys want to help support the channel, check out the Tokyo merch. And if you guys want to see more videos like this or anything related to Japan, hit that subscribe button and the bell button. I'll catch you guys.
And what vehicle searches, and is brought to us by Police Activities Channel. Be sure to check out the description below and give them the credit that they deserve. On April 7th, 2018, Officer Courtney Brown and Officer Christy Wilson of the Roswell Police Department pulled over Georgia resident Sarah Webb for allegedly speeding on her way to work in Duluth, Georgia. After Ms. Webb pulled over, Officer Brown approached the vehicle.
Stay in the car.
Sorry, my window doesn't hold.
Officer Brown, Roswell Police Department. You know how fast you were just going, ma'am?
I'm so sorry, I'm late for work.
So you could go over 80 miles per hour on 92? No, ma'am. You have your driver's license and your insurance card?
Yeah, my insurance.
Turn off the car and pass me the keys, please. The ground's wet. It's been raining. You're going over 80 miles an hour
so
on this type of a road. That's reckless driving, ma'am.
This is LexisNexis. I'm trying to look it up. I don't have it printed off.
Give me 1 second. I'll be right with you. Go for it. Hey. She was going like almost 90 down 92. Oh, really? She flew past me. I had to get up to 90 to catch her. Wow. My CAD's not working. Is yours? But did you?
I checked.
Can you see if can you check the tag too? I'm gonna have to restart this and see.
one long live stream, and I've done some for 02, 03, and 04, and there will be more here by the time you watch this video. But if you'd like to see how I figure out the solutions to the exercises, you can watch those videos and go through them yourself. But first and foremost, I would highly recommend trying out the exercises on your own first, and then if you get stuck, refer to the notebook here, refer to the PyTorch documentation, and finally, you can check out what I would have coded as a potential solution. So there's number 3, computer vision exercise solutions. So congratulations on going through the PyTorch computer vision section. I'll see you in the next section. We're going to look at PyTorch custom datasets, but no spoilers. I'll see you soon. Hello, and welcome to section number 4 of the Learn PyTorch for Deep Learning course. We have custom datasets with PyTorch. Now, before we dive into what we're going to cover, let's answer the most important question: where can you get help? Now, we've been through this a few times now, but it's important to reiterate. Follow along with the code as best you can. We're going to be writing a bunch of PyTorch code. Remember the motto: if in doubt, run the code. That's in line with try it for yourself. If you'd like to read the doc string, you can press Shift Command plus Space in Google Colab, or if you're on Windows, Command might be Control. Then if you're still stuck, you can search for it. 2 of the resources you'll probably come across is Stack Overflow or the wonderful PyTorch documentation, which we've had a lot of experience with so far. Then, of course, try again, go back through your code. If in doubt, code it out, or if in doubt, run the code. And then finally, if you're still stuck, ask a question on the PyTorch Deep Learning Discussions GitHub page. So if I click this link, we come to mrdberg/PyTorch Deep Learning. The URL is here. We've seen this before. If you have a trouble or a problem with any of the course, you can start a discussion, and you can select a category: general, ideas, polls, Q&A, and then we can go here. Video, put the video number in, so 99, for example. My code doesn't do what I'd like it to. So say your problem, and then come in here, write some code here, and then my question is something. Click Start Discussion, and then we can help out. And then if we come back to discussions, of course, you can search for what's going on. So if you have an error and you feel like someone else might have seen this error, you can, of course, search it and find out what's happening. Now, I just want to highlight again, the resources for this course are at learnpytorch.io. We are up to section 4. This is a beautiful online book version of all the materials we are going to cover in this section. So spoiler alert, you can use this as a reference. And then, of course, in the GitHub, we have the same notebook here, PyTorch Custom Datasets. This is the ground truth notebook. So check that out if you get stuck. So I'm just going to exit out of this. We've got PyTorch Custom Datasets at learnpytorch.io. And then, of course, the discussions tab for the Q&A. Now, if we jump back to the keynote, what do we have? We might be asking, what is a custom dataset? Now, we've built a fair few PyTorch deep learning neural networks so far on various datasets such as Fashion MNIST, but you might be wondering, hey, I've got my own dataset, or I'm working on my own problem. Can I build a model with PyTorch to predict on that dataset? And the answer is yes. However, you do have to go through a few pre-processing steps to make that dataset compatible with PyTorch. And that's what we're going to be covering in this section. And so, I'd like to highlight the PyTorch domain libraries. Now, we've had a little bit of experience before with Torch Vision, such as if we wanted to classify whether a photo was of pizza, steak, or sushi, so a computer vision image classification problem. Now, there's also text, such as if these reviews are positive or negative, and you can use Torch text for that. But again, these are only just one problem within the vision space, within the text space. I want you to just understand that if you have any type of vision data, you probably want to look into Torch Vision. And if you have any kind of text data, you probably want to look into Torch text. And then if you have audio, such as if you wanted to classify what song was playing, this is what Shazam does. It uses the input sound of some sort of music, and then runs a neural network over it to classify it to a certain song. You can look into Torch audio for that. And then if you'd like to recommend something, such as you have an online store, or if you're Netflix or something like that, and you'd like to have a homepage that updates for recommendations, you'd like to look into Torch Rec, which stands for Recommendation System. And so this is just something to keep in mind, because each of these domain libraries has a datasets module that helps you work with different datasets from different domains. And so different domain libraries contain data loading functions for different data sources. So Torch Vision, let's just go into the next slide. We have problem space, vision. For pre-built datasets, so existing datasets like we've seen with Fashion MNIST, as well as functions to load your own vision datasets, you want to look into torchvision.datasets. So if we click on this, we have built-in datasets. This is the PyTorch documentation. And if we go here, we have Torch Audio, Torch Text, Torch Vision, Torch Rec, Torch Data. Now, at the time of recording, which is April 2022, Torch Data is currently in beta, but it's going to be updated over time, so just keep this in mind. Updated over time to add even more ways to load different data resources. But for now, we're just going to get familiar with Torch Vision datasets. If we went into Torch Text, there's another Torch Text.datasets. And then if we went into Torch Audio, we have Torch Audio.datasets. And so you're noticing a trend here that depending on the domain you're working in, whether it be vision, text, audio, or your data is recommendation data, you'll probably want to look into its custom library within PyTorch. And of course, the bonus is Torch Data. It contains many different helper functions for loading data and is currently in beta as of April 2022. So by the time you watch this, Torch Data may be out of beta, and then that should be something that's extra curriculum on top of what we're going to cover in this section. So let's keep going. So this is what we're going to work towards building. Food Vision Mini. So we're going to load some data, namely some images of pizza sushi, and steak from the Food 101 dataset. We're going to build an image classification model, such as the model that might power a food vision recognition app or a food image recognition app. And then we're going to see if it can classify an image of pizza as pizza, an image of sushi as sushi, and an image of steak as steak. So this is what we're going to focus on. We want to load, say we had images existing already of pizza, sushi, and steak. We want to write some code to load these images of food, so our own custom data set for building this food vision mini model, which is quite similar to if you go to, this is the project I'm working on personally, Nutrify.app. This is a food image recognition model. Here we go. So it's still a work in progress as I'm going through it, but you can upload an image of food and Nutrify will try to classify what type of food it is. So do we have steak? There we go. Let's upload that.
See what the deal is. I'm gonna take her probably for reckless.
Okay.
She flew past me going probably 80, 85 on 92 in the wet road. She said she's running late for work. I had to get up to 90 to catch her. What do you think? I mean, I don't have any speed detection, so at the same time, but...
Here, Officer Brown admits that she was not equipped with any speed detection devices to get an accurate measurement of Ms. Webb's speed. While the law varies between states, in Georgia, individuals can be convicted of speeding or reckless driving based purely on an officer's visual estimate of their speed. Georgia's speeding laws are found in Section 40-6-180 of the Georgia Code, which reads that, quote, "No person shall drive a vehicle at a speed greater than is reasonable and prudent under the conditions, and having regard for the actual and potential hazards then existing." And Section 40-6-181, which states that no person shall drive a vehicle at a speed in excess of certain maximum limits. In the 1992 case of Brown versus State, the Court of Appeals of Georgia determined that an officer's testimony
Stay in the car.
Sorry, my window doesn't hold.
Off to Brown.
Off.
Restart my computer. Thank you. I don't have any speed detection, so at the same time, but...
90.
Yeah, I mean, that's unacceptable. I told her, I said, you know the roads are wet, correct? You're running late for work and you're going above 80 to get to work. I said, call. So do not do that and put people's lives in jeopardy.
Yeah.
So, my CAD just froze on me, so I'm restarting it right now. What do you think? Or just tickets?
Atlanta answer or Roswell answer?
Hold on. Are you? Okay, hold on. Thank you.
Valid.
Yeah, sorry, she did it. Unavailable. My CAD's not working. Who's that?
A head, R tail.
Okay.
This is tail, right?
Yeah, so really.
23.
Michael Jordan? Hi. So I got too fast for, let me write this down.
Too fast for conditions.
Is it
Right
reckless?
Yeah, you can do reckless, and then speeding. And you're just gonna have to mark the pace one instead of the...
I mean,
then
either way, the speed limit here is what, 45?
Yeah.
45.
She was going way.
Super
I
speed.
mean, because I haven't done one like speeding like that, so that's
So
why
you're
I'm
gonna
a little bit
you're gonna
unsure.
do the patrol vehicle spot, and then it's gonna ask you for moving or not moving, and you're gonna do moving.
Can you help me do these dang tickets? My CAD won't even log me in. Sorry. Alright, I'm gonna go. Yeah, that's not okay. Yeah. Alright, man. Do me a favor and step out of the vehicle for me. Put the phone down.
Why am I
Put your
doing
phone down. Step out of the vehicle. Turn around. Put your hands behind your back. Because, ma'am, you're driving entirely too fast for conditions. You put a lot of people's lives in jeopardy, okay? Double locking these so that they don't tighten on you. Do me a favor and step in front of my vehicle, ma'am. step in front of my patrol vehicle. Do you have anything? Do you have anything? Do you have anything in your pockets? Do you have anything on you? Poke, stick, or stab me? Any drugs, paraphernalia, anything like that? Okay. You have a bond. Okay, turn to the side for me. Here, move Humbercast. I'm just gonna shake this out, okay? Alright. Do me a favor, step over here. It's my patrol vehicle. Have a seat for me. We're gonna buckle you in, okay?
Beautiful. Steak. So we're going to be building a similar model to what powers Nutrify. And then there's the macronutrients for the steak, yada, yada, yada. If you'd like to find out how it works, I've got all the links here, but that's at nutrify.app. So let's keep pushing forward. We'll go back to the keynote. This is what we're working towards. As I said, we want to load these images into PyTorch so that we can build a model. We've already built a computer vision model. So we want to figure out how do we get our own data into that computer vision model. And so, of course, we'll be adhering to our PyTorch workflow that we've used a few times now. So we're going to learn how to load a data set with our own custom data rather than an existing data set within PyTorch. We'll see how we can build a model to fit our own custom data set. We'll go through all the steps that's involved in training a model, such as picking a loss function and an optimizer. We'll build a training loop. We'll evaluate our model. We'll improve through experimentation. And then we can see save and reloading our model, but we're also going to practice predicting on our own custom data, which is a very, very important step whenever training your own models. So what we're going to cover broadly, we're going to get a custom data set with PyTorch, as we said. We're going to become one with the data. In other words, preparing and visualizing it. We'll learn how to transform data for use with a model, very important step. We'll see how we can load custom data with pre-built functions and our own custom functions. We'll build a computer vision model, aka Food Vision Mini, to classify pizza, steak, and sushi images, so a multi-class classification model. We'll compare models with and without data augmentation. We haven't covered that yet, but we will later on. And finally, we'll see how we can, as I said, make predictions on custom data. So this means data that's not within our training or our test data set. And how are we going to do it? Well, we could do it cooks or chemists, but I like to treat machine learning as a little bit of an art, so we're going to be cooking up lots of code. With that being said, I'll see you in Google Colab. Let's code. Welcome back to the PyTorch Cooking Show. Let's now learn how we can cook up some custom data sets. I'm going to jump into Google Colab, so colab.research.google.com. And I'm going to click New Notebook. Just going to make sure this is zoomed in enough for the video. Wonderful. So I'm going to rename this notebook 04, because we're up to section 04. And I'm going to call it PyTorch Custom Datasets _ video, because this is going to be one of the video notebooks, which has all the code that I write during the videos, which is, of course, contained within the video notebooks folder on the PyTorch Deep Learning repo. So if you'd like the resource or the ground truth notebook for this, I'm going to just put a heading here, 04 PyTorch Custom Datasets Video Notebook. Make that bigger. And then we'll put resources. So book version of the course materials for 04. We'll go there. And then we'll go ground truth version of notebook 04, which will be the reference notebook that we're going to use for this section. Come into PyTorch Custom Datasets, and then we can put that in there. Wonderful. So the whole synopsis of this custom dataset section is we've used some datasets with PyTorch before, but how do you get your own data into PyTorch? Because that's what you want to start working on, right? You want to start working on problems of your own. You want to come into any sort of data that you've never worked with before, and you want to figure out how do you get that into PyTorch. So one of the ways to do so is via custom datasets. And then I want to put a note down here. So we're going to go 0, section 0 is going to be importing PyTorch and setting up device agnostic code. But I want to just stress here that domain libraries. So just to reiterate what we went through last video, so depending on what you're working on, whether it be vision, text, audio, recommendation, something like that, you'll want to look into each of the PyTorch domain libraries for existing data loader or data loading functions and customizable data loading functions. So just keep that in mind. We've seen some of them. So if we go Torch Vision, which is what we're going to be looking at, Torch Vision, we've got data sets and we've got documentation. We've got data sets for each of the other domain libraries here as well. So if you're working on a text problem, it's going to be a similar set of steps to what we're going to do with our vision problem when we build Food Vision Mini. what we have is a data set that exists somewhere, and what we want to do is bring that into PyTorch so we can build a model with it. So let's import the libraries that we need. So we're going to import Torch, and we'll probably import NN. So we'll import that from PyTorch, and I'm just going to check the Torch version here. So note, we need PyTorch 1.10.0 plus is required for this course. So if you're using Google Colab at a later date, you may have a later version of PyTorch. I'm just going to show you what version I'm using. Just going to let this load. We're going to get this ready. We're going to also set up device agnostic code right from the start this time, because this is best practice with PyTorch. So this way, if we have a CUDA device available, our model is going to use that CUDA device, and our data is going to be on that CUDA device. So there we go, wonderful. We've got PyTorch 1.10.0 plus CUDA 1.11, maybe that's 11.1. So let's check if CUDA dot is available. Now, I'm using Google Colab. We haven't set up a GPU yet, so it probably won't be available yet. Let's have a look. Wonderful. So because we've started a new Colab instance, it's going to use the CPU by default. So how do we change that? We come up to runtime, change runtime type. I'm going to go hardware accelerator, GPU. We've done this a few times now. I am paying for Google Colab Pro. So one of the benefits of that is that Google Colab reserves faster GPUs for you. You do not need Google Colab Pro, as I've said, to complete this course. You can use the free version, but just recall Google Colab Pro tends to give you a better GPU just because GPUs aren't free. Wonderful. So now we've got access to a GPU. CUDA, what GPU do I have? NVIDIA SMI, I have a Tesla P100 with 16 gigabytes of memory, which will be more than enough for the problem that we're going to work on in this video. So I believe that's enough to cover for the first coding video. Let's, in the next section, we are working with custom data sets after all. Let's, in the next video, let's get some data, hey? Now, as I said in the last video, we can't cover custom data sets without some data. So let's get some data and just remind ourselves what we're going to build, and that is Food Vision Mini. So we need a way of getting some food images. And if we go back to Google Chrome, Torch Vision datasets has plenty of built-in datasets, and one of them is the Food 101 dataset. Food 101. So if we go in here, this is going to take us to the original Food 101 website. So Food 101 is 101 different classes of food. It has a challenging dataset of 101 different food categories with 101,000 images. So that's quite a beefy dataset. And so for each class, 250 manually reviewed test images are provided. So we have per class, 101 classes, 250 testing images, and we have 750 training images. Now, we could start working on this entire dataset straight from the get-go, but to practice, I've created a smaller subset of this dataset, and I'd encourage you to do the same with your own problems. Start small and upgrade when necessary. So I've reduced the number of categories to 3, and the number of images to 10%. Now, you could reduce this to an arbitrary amount, but I've just decided 3 is enough to begin with, and 10% of the data. And then if it works, hey, you could upscale that on your own accord. And so I just want to show you the notebook that I used to create this dataset, and as extra curriculum, you could go through this notebook. So if we go into extras, 04 custom data creation. This is just how I created the subset of data. So making a dataset to use with notebook number 4, I created it in custom image dataset or image classification style. So we have a top level folder of pizza, steak, and sushi. We have a training directory with pizza, steak, and sushi images. And we have a test directory with pizza, steak, and sushi images as well. So you can go through that to check it out how it was made. But now, and also, if you go to learnpytorch.io, section 4, there's more information here about what Food 101 is. So get data, here we go. There's all the information about Food 101. There's some resources, the original Food 101 dataset, Torch Vision datasets, Food 101, how I created this dataset, and actually downloading the data. But now we're going to write some code because this dataset, the smaller version that I've created, is on the PyTorch Deep Learning repo under data, and then we have pizza steak sushi.zip. Oh, this one is a little spoiler for one of the exercises for this section, but You'll see that later. So let's go in here. Let's now write some code to get this data set from GitHub, pizzasteaksushi.zip, and then we'll explore it. We'll become one with the data. So I just want to write down here, our data set is a subset of the Food 101 data set. Food 101 starts with 101 different classes of food. So we could definitely build computer vision models for 101 classes, but we're going to start smaller. Our data set starts with 3 classes of food and only 10% of the images. So let's write here, and 1,000 images per class, which is 750 training, 250 testing, and we have about 75 training images per class and about 25 testing images per class. So why do this? When starting out ML projects, it's important to try things on a small scale and then increase the scale when necessary. The whole point is to speed up how fast you can experiment. Because there's no point trying to experiment on things that if we try to train on 100,000 images to begin with, our models might take half an hour to train at a time. So at the beginning, we want to increase the rate that we experiment at. And so let's get some data. We're going to import requests so that we can request something from GitHub to download this URL here. Then we're also going to import zip file from Python because our data is in the form of a zip file right now. Then we're going to get pathlib because I like to use paths whenever I'm dealing with file paths or directory paths. So now let's set up a path to a data folder. And this, of course, will depend on where your data set lives, what you'd like to do, but I typically like to create a folder over here called data, and that's just going to store all of my data for whatever project I'm working on. So data path equals path data, and then we're going to go image path equals data path slash pizza steak sushi. We're going to have images from those 3 classes. Pizza, steak, and sushi are 3 of the classes out of the 101 in Food 101. So if the image folder doesn't exist, so if our data folder already exists, we don't want to re-download it. But if it doesn't exist, we want to download it and unzip it. So if image path is dir, so we want to print out the image path directory already exists, skipping download. And then if it doesn't exist, we want to print image path does not exist, creating one. Beautiful. And so we're going to go image path.mkdir to make a directory. We want to make its parents if we need to the parent directories, and we want to pass exist OK equals true so we don't get any errors if it already exists. And so then we can write some code. I just want to show you what this does if we run it. So our target directory data slash pizza steak sushi does not exist. It's creating one. So then we have now data and inside pizza steak sushi. Wonderful. But we're going to fill this up with some images so that we have some data to work. And we have now, and the whole premise on it. But I just want to stress that this step will be very similar no matter what data you're working with. You'll have some folder over here, or maybe it'll live on the cloud somewhere. Who knows, wherever your data is, but you'll want to write code to load it from here into PyTorch. So let's download pizza, steak, and sushi data. So I'm going to use with. I'll just X over here so we have more screen space. With open, I'm going to open the data path slash the file name that I'm trying to open, which will be pizzasteaksushi.zip, and I'm going to write binary as F. So this is essentially saying I'm doing this in advance because I know I'm going to download this folder here. So I know the file name of it, pizzasteaksushi.zip. I'm going to download that into Google Colab, and I want to open it up. So request equals request.get. And so when I want to get this file, I can click here. And then if I click download, it's going to, what do you think it's going to do? Well, let's see. If I wanted to download it locally, I could do that. And then I could come over here, and then I could click upload if I wanted to. So upload to session storage, I could upload it from that, but I prefer to write code so that I could just run this cell over again and have the file, instead of being downloaded to my local computer, it just goes straight into Google Colab. So to do that, we need the URL from here, and I'm just going to put that in there. It needs to be as a string. Excuse me. I'm getting trigger happy on the shift and enter. Wonderful. So now I've got a request to get the content that's in here. And GitHub can't really show this because this is a zip file of images. Spoiler alert. Now let's keep going. We're going to print out that we're downloading pizza, steak, and sushi data. ... And then I'm going to write to file the request.content. So the content of the request that I just made to GitHub. So that's request is here, using the Python request library to get the information here from GitHub. This URL could be wherever your file is being stored. And then I'm going to write the content of that request to my target file, which is this. This here. So if I just copy this, I'm going to write the data to here. Data path / pizza steak sushi zip. And then because it's a zip file, I want to unzip it. So unzip pizza steak sushi data. Let's go with zip file. So we imported zip file up there, which is a Python library to help us deal with zip files. I'm going to use zipfile.zip file. I'm going to pass it in the data path. So just the path that we did below. Data path / pizza steak sushi .zip. And this time, instead of giving it write permissions, so that's what WB stands for. It stands for write binary. I'm going to give it read permissions. So I want to read this target file instead of writing it. And I'm going to go as zipref. We could call this anything really, but zipref is kind of, you'll see this a lot in different Python examples. So we're going to print out again. So unzipping pizza, steak, and sushi data. Then we're going to go zip _ref .extract all. And we're going to go image path. So what this means is it's taking the zipref here, and it's extracting all of the information that's within that zipref, so within this zip file, to the image path, which is what we created up here. So if we have a look at image path, let's see that. Image path. Wonderful. So that's where all of the contents of that zip file are going to go into this file. So let's see it in action. You ready? Hopefully it works. 3, 2, 1, run. File is not a zip file. Oh no, what did we get wrong? So, did I type this wrong? .zip, data path. Oh, we got the zip file here. Pizza steak sushi .zip, read, data path. Okay, I found the error. So this is another thing that you'll have to keep in mind, and I believe we've covered this before, but I like to keep the errors in these videos so that you can see where I get things wrong, because you never write code right the first time. So we have this link in GitHub. We have to make sure that we have the raw link address. So if I come down to here and copy the link address from the download button, you'll notice a slight difference if we come back into here. So I'm just going to copy that there. So if we step through this, GitHub, Mr. Debug, PyTorch Deep Learning, we have raw instead of blob. So that is why we've had an error, is that our code is correct. It's just downloading the wrong data. So let's change this to the raw. So just keep that in mind. You must have raw here. And so let's see if this works. Do we have the correct data? Oh, we might have to delete this. Oh, there we go. Test. Beautiful. Train. Pizza, steak, sushi, wonderful. So it looks like we've got some data, and if we open this up, what do we have? We have various JPEGs. Okay, so this is our testing data. And if we click on there, we've got an image of pizza. Beautiful. So we're going to explore this a little bit more in the next video, but that is some code that we've written to download datasets, or download our own custom dataset. Now, just recall that we are working specifically on a pizza, steak, and sushi problem for computer vision. However, our whole premise is that we have some custom data, and we want to convert these. How do we get these into tensors? That's what we want to do. And so the same process will be for your own problems. We'll be loading a target dataset and then writing code to convert whatever the format the dataset is in into tensors for PyTorch. So I'll see you in the next video. Let's explore the data we've downloaded. Welcome back. In the last video, we wrote some code to download a target dataset, our own custom dataset from the PyTorch Deep Learning data directory. And if you'd like to see how that dataset was made, you can go to PyTorch Deep Learning/extras. It's going to be in the custom data creation notebook here for 04. So I've got all the code there. All we've done is take data from the Food 101 dataset, which you can download from this website here, or from Torch Vision. So if we go to Torch Vision Food 101, we've got the dataset built into PyTorch there. So I've used that dataset from PyTorch and broken it down from 101 classes to 3 classes so that we can start with a small experiment. So there we go. Get the training data, datasets Food 101, and then I've customized it to be my own style. So if we go back to Colab, we've now got pizza, steak, sushi, a test folder, which will be our testing images, and a train folder, which will be our training images. This data is in standard image classification format, but we'll cover that in a second. What we're going to do in this video is kick off section number 2, which is becoming one with the data, which is one of my favorite ways to refer to data preparation and data exploration. So becoming one with the data. And I'd just like to show you one of my favorite quotes from Abraham Loss Function. So if I had 8 hours to build a machine learning model, I'd spend the first 6 hours preparing my dataset. And that's what we're going to do. Abraham Loss Function sounds like he knows what is going on, but since we've just downloaded some data, let's explore it, hey? And we'll write some code now to walk through each of the directories. How you explore your data will depend on what data you've got. So we've got a fair few different directories here with a fair few different folders within them. So how about we walk through each of these directories and see what's going on? If you have visual data, you probably want to visualize an image. So we're going to do that in a second too. We'll write a little doc string for this helper function. So walks through dir path, returning its contents. Now, just in case you didn't know, Abraham Loss Function does not exist as far as I know, but I did make up that quote. So we're going to use the os.walk function, os.walk, and we're going to pass it in a dir path. And what does walk do? We can get the doc string here. Directory tree generator. For each directory in the directory tree, rooted at the top, including top itself, but excluding dot and dot dot, yields a 3-tuple: dir path, dir names, and file names. You can step through this in the Python documentation if you'd like, but essentially it's just going to go through our target directory, which in this case will be this one here, and walk through each of these directories, printing out some information about each one. So let's see that in action. This is one of my favorite things to do if we're working with standard image classification format data. So there are length dir names, directories, and let's go len, file names. I say it length like I've got the G on the end, but it's just len. Images in, let's put in here, dir path. So a little bit confusing if you've never used walk before, but it's so exciting to see all of the information in all of your directories. Oh, we didn't run it. Let's check our function now. Walk through dir, and we're going. To pass it in the image path, which is what? Well, it's going to show us. Oh, beautiful. So let's compare what we've got in our printout here. There are Well, it's going to show us. Oh, beautiful. So let's compare what we've got in our printout here. There are 2 directories and 0 images in data, pizza, steak, sushi. So this one here, there's 0 images, but there's 2 directories. Test and train, wonderful. And there are 3 directories in data, pizza, steak, sushi, test. Yes, that looks correct. 3 directories, pizza, steak, sushi. And then we have 0 directories and 19 images in pizza, steak, sushi / test, steak. If we have a look at this. So that means there's 19 testing images for steak. Let's have a look.
RDR 390R. Alpha 1 in custody. Alpha 1, can you please start me at 85? How does this open? Perfume.
Alpha 189.
Sunglasses. Times 2.
is 92 and Bentgrass, and you're at the post office. All right.
Okay.
Losing possession here, and he's broken free. And a goal! The quick 1-2, and they've turned this game on its head.
They're not trying to pit him or anything because he's driving through residential neighborhoods. If he was on the interstate and it was kind of clear, they'd probably try to pit him. Maybe it's California. Dude, that El Camino fucked. You guys see that?
Epileptic seizure and be injured or really point.
Do you flip?
Because under occupation, it says Jack is an invalid.
It's also thought to be the first painting of Indians done in Europe. The Virgin's Cape seems to protect everyone under it, even the Indians. Like the palace, the gardens reflect a mix of cultures. The intimate geometric Moorish gardens lead to the later, much more expansive backyard of Spanish kings. The gardens are full of tropical flowers, cool fountains, and, in the summer, hot tourists. I'm thankful we're here in late April, beating the brutal heat of the Andalusian summer. The Moors were relatively tolerant of other religions. During their rule, Christians, Jews, and Muslims shared the city peacefully. After the Christian reconquest, Sevilla's thriving Jewish community was concentrated here in the Barrio de Santa Cruz. Today, only a few peaceful squares surrounded by a tangled web of alleys survives from the days when this was Sevilla's Jewish quarter. Explore. Wander among lanes too narrow for cars, whitewashed houses corralling peaceful squares, and wrought iron latticework. Regardless of who lived here, the design of the neighborhood seems to have one goal: stay cool. The narrow streets, some with buildings so close they're called kissing lanes, were designed to maximize shade. Homes faced an inner courtyard, offering a welcome refuge from the bustle and summer heat. The Moors gave Andalusia its characteristic glazed tiles with only geometric patterns. In later centuries, Christians decorated their tiles with livelier scenes. Either way, the tiles kept buildings cooler.
Look at one of them. There we go. Now, again, these are from the Food 101 dataset, the original Food 101 dataset, which is just a whole bunch of images of food. 100,000 of them, there's some steak there, wonderful. And we're trying to build a food vision model to recognize what is in each image. Then if we jump down to here, we have 3 directories in the training directory. So we have pizza, steak, sushi, and then we have 75 steak images, 72 sushi images, and 78 pizza. So slightly different, but very much the same numbers. They're not too far off each other. So we've got about 75 or so training images, and we've got about 25 or so testing images per class. Now, these were just randomly selected from the Food 101 dataset, 10% of 3 different classes. So let's keep pushing forward, and we're going to set up our training and test paths. So I just want to show you, we'll just set up this, and then I'll just show you the standard image classification setup. Image path.train, and we're going to go tester. So if you're working on an image classification problem, we want to set this up as test. And then if we print out the trainer and the tester, this is what we're going to be trying to do. We're going to write some code to go, hey, look at this path for our training images, and look at this path for our testing images. And so this is the standard image classification data format, is that you have your overall dataset folder, and then you have a training folder dedicated to all of the training images that you might have, and then you have a testing folder dedicated to all of the testing images that you might have. And you could have a validation dataset here as well if you wanted to. But to label each one of these images, the class name is the folder name. So all of the pizza images live in the pizza directory. The same for steak, and the same for sushi. So depending on your problem, your own data format will depend on whatever you're working on. You might have folders of different text files or folders of different audio files. But the premise remains, we're going to be writing code to get our data here into tensors for use with PyTorch. And so where does this come from, this image data classification format? Well, if we go to the TorchVision.datasets documentation, as you start to work with more datasets, you'll start to realize that there are standardized ways of storing specific types of data. So if we come down to here, base classes for custom datasets, we'll be working towards using this image folder dataset. But this is a generic data loader where the images are arranged in this way by default. So I've specifically formatted our data to mimic the style that this pre-built data loading function is for. So we've got a root directory here in case of we were classifying dog and cat images. We have root, then we have a dog folder, then we have various images, and the same thing for cat. This would be dog versus cat. But the only difference for us is that we have food images and we have pizza, steak, sushi. If we wanted to use the entire Food 101 dataset, we would have 101 different folders of images here, which is totally possible, but to begin with, we're keeping things small. So let's keep pushing forward. As I said, we're dealing with a computer vision problem. So what's another way to explore our data other than just walking through the directories themselves? Let's visualize an image, hey? But we've done that before with just clicking on the file. How about we write some code to do so? We'll replicate this, but with code. I'll see you in the next video. Welcome back. In the last video, we started to become one with the data. And we learned that we have about 75 images per training class and about 25 images per testing class. And we also learned that the standard image classification data structure is to have the steak images within the steak folder of the training dataset, and the same for test, and the pizza images within the pizza folder, and so on for each different image classification class that we might have. So if you want to create your own dataset, you might format it in such a way that your training images are living in a directory with their classification name. So if you wanted to classify photos of dogs and cats, you might create a training folder of train/dog, train/cat, put images of dogs in the dog folder, images of cats in the cat folder, and the same for the testing dataset. But the premise remains, I'm going to sound like a broken record here. We want to get our data from these files, whatever files they may be in, whatever data structure they might be in, into tensors. But before we do that, let's keep becoming one with the data, and we're going to visualize an image. So visualizing an image, and you know how much I love randomness. So let's select a random image from all of the files that we have in here, and let's plot it, hey? Because we could just click through them and visualize them, but I like to do things with code. So specifically, let's plan this out. Let's write some code to, number one is get all of the image paths. We'll see how we can do that with the path lib library. We then want to pick a random image path using, we can use Python's random for that. Python's random.choice, we'll pick a single image, random.choice. Then we want to get the image class name. And this is where pathlib comes in handy. Class name, recall that whichever target image we pick, the class name will be whichever directory that it's in. So in the case of if we picked a random image from this directory, the class name would be pizza. So we can do that using, I think it's going to be pathlib.path, and then we'll get the parent folder, wherever that image lives. So the parent image, parent folder, the parent directory of our target random image. And we're going to get the stem of that. So we have stem. The stem is the last little bit here. Number 4, what should we do? Well, we want to open the image. So since we're working with images, let's open the image with Python's pill, which is Python image library, but will actually be pillow. So if we go Python pillow, a little bit confusing when I started to learn about Python image manipulation. So pillow is a friendly pill fork, but it's still called pill. So just think of pillow as a way to process images with Python. So pill is the Python imaging library by Frederick Lund. And so Alex Clark and contributors have created pillow. So thank you, everyone. And let's go to number 5. What do we want to do as well? We want to, let's get some metadata about the image. We'll then show the image and print metadata. Wonderful. So let's import random, because machine learning is all about harnessing the power of randomness, and I like to use randomness to explore data as well as model it. So let's set the seed. So we get the same image on both of our ends. So random.seed. I'm going to use 42. You can use whatever you'd like, but if you'd like to get the same image as me, I'd suggest using 42 as well. Now let's get all the image paths. So we can do this because our image path list, we want to get our image path. So recall that our image path is this. So this folder here, I'm just going to close all this. So this is our image path, this folder here. You can also go copy path if you wanted to. We're just going to get something very similar there. That's going to error out, so I'll just comment that. So it doesn't error. That's our path, but we're going to keep it in the POSIX path format. And we can go list. Let's create a list of imagepath.glob, which stands for grab. I don't actually know what glob stands for, but to me it's like glob together all of the images or all of the files that suit a certain pattern. So glob together for me means stick them all together. And you might be able to correct me if I've got the wrong meaning there. I'd appreciate that. And so we're going to pass in a certain combination. So we want star /star, and then we want star.jpg. Now, why are we doing this? Well, because we want every image path. So star is going to be this first directory here. So any combination, it can be train or test. And then this star means anything for what's inside test. So let's say this first star is equal to test. This second star is equal to anything here. So it could be any of pizza, steak, or sushi. And then finally this star, let's say it was test, pizza. This star is anything in here that is before .jpg. So it could be any one of these files here. Now, this will make more sense once we print it out. So image path list. Let's have a look. There we go. So now we've got a list of every single image that's within pizza, steak, sushi. And this is just another way that I like to visualize data, is to just get all of the paths and then randomly visualize it, whether it be an image or text or audio. You might want to randomly listen to it. Recall that each of the domain libraries have different input and output methods for different data sets. So if we come to Torch Vision, we have utils, so we have different ways to draw on images, reading and writing images and videos. So we could load an image via read image, we could decode it, we could do a whole bunch of things. I'll let you explore that as extra curriculum. But now let's select a random image from here and plot it. So we'll go number 2, which was our step up here. Pick a random image. So pick a random image path. Let's get rid of this. And so we can go random image path equals random.choice. Harness the power of randomness to explore our data. Let's get a random image from image path list, and then we'll print out random image path. Which one was our lucky image that we selected? Beautiful. So we have a test pizza image as our lucky random image. And because we've got a random seed, it's going to be the same one each time. Yes, it is. And if we comment out the random seed, we'll get a different one each time. We've got a steak image. We've got another steak image. Another steak image. Oh, 3 in a row. 4 in a row. Pizza. Okay, let's keep going. So we'll get the image class from the path name. So the image class is the name of the directory, because our image data is in standard image classification format, where the image is stored. So let's do that. Image class equals random image path dot parent dot stem, and then we're going to print image class. What do we get? So we've got pizza, wonderful. So the parent is this folder here, and then the stem is the end of that folder, which is pizza. Beautiful. Well, now what are we up to now? We're working with images. Let's open up the image. So we can open up the image using pill. We can also open up the image with PyTorch here, so with read image, but we're going to use pill to keep things a little bit generic for now. So open image, image equals image. So from pill import image, and the image class has an open function, and we're just going to pass it in here, the random image path. Note, if this is corrupt, if your image is corrupt, this may error. So then you could potentially use this to clean up your data set. I've imported a lot of images with image.open of our target data set here. I don't believe any of them are corrupt, but if they are, please let me know. And we'll find out later on when our model tries to train on it. So let's print some metadata. So when we open our image, we get some information from it. So let's go, our random image path is what? Random image path. We're already printing this out, but we'll do it again anyway. And then we're going to go, the image class is equal to what? Will be the image class. Wonderful. And then we can print out, we can get some metadata about our images. So the image height is going to be img.height. We get that metadata from using the pill library. And then we're going to print out image width, and we'll get img.width, and then we'll print the image itself. Wonderful. And we can get rid of this, and we can get rid of this. Let's now have a look at some random images from our self. Wonderful. And we can get rid of this, and we can get rid of this. Let's now have a look at some random images from our dataset. Lovely, we've got an image of pizza there. Now, I will warn you that one of the downsides of working with food data is it does make you a little bit hungry. So there we've got some sushi, and then we've got some more sushi, some steak, And we have a steak. We'll go one more for good luck. And we finish off with some sushi. Oh, that could be a little bit confusing to me. I thought that might be... be steak to begin with. And this is, do you see now, we'll do one more, why it's important to sort of visualize your images randomly, because you never know what you're going to come across. And this way, once we visualize enough images, you could do this 100 more times, you could do this 20 more times, until you feel comfortable to go, hey, I feel like I know enough about the data now. Let's see how well our model goes on this sort of data. So we'll finish off on this steak image. And now I'll set you a little challenge before the next video, is to visualize an image like we've done here, but this time do it with Matplotlib. So try to visualize an image with Matplotlib. That's your little challenge before the next video, so give that a go. We want to do a random image as well, so quite a similar setup to this, but instead of printing out things like this, we want to visualize it using Matplotlib. So try that out, and we'll do it together in the next video. Oh, we are well on the way to creating our own PyTorch custom dataset. We've started to become one with the data. But now, let's continue to visualize another image. I set you the challenge in the last video to try and replicate what we've done here with the pill library with Matplotlib. So now, let's give it a go, hey? And why use Matplotlib? Well, because Matplotlib, and I'm going to import NumPy as well, because we're going to have to convert this image into an array. That was a little trick that I didn't quite elaborate on, but I hope you tried to decode it out and figured it out from the errors you received. But Matplotlib is one of the most fundamental data science libraries, so you're going to see it everywhere. So it's just important to be aware of how to plot images and data with Matplotlib. So turn the image into an array. So we can go image as array, and I'm going to use the NumPy method, np as array. We're going to pass it in the image. Recall that the image is the same image that we've just set up here, and we've already opened it with pill. And then I'm going to plot the image. So plot the image with Matplotlib, plt.figure, and then we can go fig size equals 10, 7, and then we're going to go plt.imshow, image as array, pass it in the array of numbers. I'm going to set the title here as an f string, and then I'm going to pass in image class equals image class. Then I'm going to pass in image shape. So we can get the shape here. Now, this is another important thing to be aware of your different data sets when you're exploring them, is what is the shape of your data? Because what's one of the main errors in machine learning and deep learning? It's shape mismatch issues. So if we know the shape of our data, we can start to go, turn the axes off here. Beautiful. So look at what we've got. Now, I've just thrown this in here without really explaining it, but we've seen this before in the computer vision section, is our image shape is 512, 306, 3. Now, the dimensions here are height is 512 pixels, the width is 306 pixels, and it has 3 color channels. So what format is this? This is color channels last, which is the default for the PIL library. And there's also the default for Matplotlib, but PyTorch, recall, is default if we put the color channels at the start, color channels first. Now, there is a lot of debate, as I've said, over which is the best order. It looks like it's leading towards going towards this, but for now, PyTorch defaults to color channels first. But that's okay, because we can manipulate these dimensions to what we need for whatever code that we're writing. And the 3 color channels is what? Red, green, and blue. So if you combine red, green, and blue in some way, shape, or form, you get the different colors here that represent our image. And so if we have a look at our image as array, our image is in numerical format. Wonderful. So, okay, we've got one way to do this for one image. I think we start moving towards scaling this up to do it for every image in our data folder. So let's just finish off this video by visualizing one more image. What do we get? Same premise, the image is now as an array, different numerical values. We've got a delicious looking pizza here of shape 512, 512 with color channels last, and we've got the same thing up here. So that is one way to become one with the data, is to visualize different images, especially random images. You could do the same thing visualizing different text samples that you're working with or listening to different audio samples. It depends what domain you're working in. So now in the next video, let's start working towards turning all of the images in here. Now that we've visualized some of them and become one with the data, we've seen that the shapes are varying in terms of height and width, but they all look like they have 3 color channels because we have color images. But now we want to write code to turn all of these images into PyTorch tensors. So let's start moving towards that. I'll see you in the next video. Hello, and welcome back. In the last video, we converted an image to a NumPy array, and we saw how an image can be represented as an array. But what if we'd like to get this image from our custom dataset over here, pizza steak sushi, into PyTorch? Well, let's cover that in this video. So I'm going to create a new heading here, and it's going to be transforming data. And so what we'd like to do here is, I've been hinting at it the fact the whole time, is we want to get our data into tensor format because that is the data type that PyTorch accepts. So let's write down here, before we can use our image data with PyTorch, now this goes for images, other vision data, it goes for text, it goes for audio, basically whatever kind of data set you're working with, you need some way to turn it into tensors. So that's step number 1, turn your target data into tensors. In our case, it's going to be a numerical representation of our images. And number 2 is turn it into a torch.utils.data.dataset. So recall from a previous video that we've used the dataset to house all of our data in tensor format. And then subsequently, we've turned our datasets, our PyTorch datasets, into torch.utils.data.dataLoader. And a data loader creates an iterable or a batched version of our dataset. So for short, we're going to call these dataset and data loader.
Is an expert.
Now, as I discussed previously, if we go to the PyTorch documentation, Torch Vision, for Torch Vision, this is going to be quite similar for Torch Audio, Torch Text, Torch Rec, Torch Data eventually when it comes out of beta. There are different ways to create such datasets. So we can go into the datasets module, and then we can find built-in datasets, and then also base classes for custom datasets. But if we go into here, image folder, there's another parameter I'd like to show you, and this is going to be universal across many of your different data types, is the transform parameter. Now, the transform parameter is a parameter we can use to pass in some transforms on our data. So when we load our datasets from an image folder, it performs a transform on those data samples that we've sent in here as the target data folder. Now, this is a lot more easier to understand through illustration rather than just talking about it. So let's create a transform. And the main transform we're going to be doing is transforming our data, and we're turning it into tensors. So let's see what that looks like. So we're just going to re-import all of the main libraries that we're going to use. So from torch utils.data, let's import data loader. And we're going to import from Torch Vision. I'm going to import data sets, and I'm also going to import transforms. Beautiful. And I'm going to create another little heading here. This is going to be 3.1, transforming data with torchvision.transform. So the main transform we're looking to here is turning our images from JPEGs. If we go into train, and then we go into any folder, we've got JPEG images. And we want to turn these into tensor representation. So there's some pizza there. We'll get out of this. Let's see what we can do. How about we create a transform here, write a transform for image, and let's start off by calling it data transform, and I'm going to show you how we can combine a few transforms together. If you want to combine transforms together, you can use transforms.compose. You can also use nn.sequential to combine transforms. But we're going to stick with transforms.compose for now, and it takes a list, and so let's let's just run out 3 transforms to begin with, and then we can talk about them after we do so. So we want to resize our images to 6464. Now, why might we do this? Well, do you recall in the last section, computer vision, we used the TinyVGG architecture? And what size were the images that the TinyVGG architecture took? Well, we replicated the CNN website version, or the CNN Explainer website version, and they took images of size 6464. So perhaps we want to leverage that computer vision model later on. So we're going to resize our images to 6464. And then we're going to create another transform. And so this is, I just want to highlight how transforms can help you manipulate your data in a certain way. So if we wanted to flip the images, which is a form of data augmentation, in other words, artificially increasing the diversity of our data set, we can flip the images randomly on the horizontal. So transforms.random horizontal flip. And I'm going to put a probability in here of p equals 0.5. So that means 50% of the time, if an image goes through this transform pipeline, it will get flipped on the horizontal axis. As I said, this makes a lot more sense when we visualize it. So we're going to do that very shortly. And finally, we're going to turn the image into a torch tensor. So we can do this with transforms.toTensor. And now, where might you find such transforms? So this transform here says toTensor. If we have a look at the doc string, we've got convert a PIL image, which is what we're working with right now, or a NumPy array to a tensor. This transform does not support torch script. If you'd like to find out what that is, I'd like to read the documentation for that. It's essentially turning your PyTorch code into a Python script. It converts a PIL image or a NumPy array from height, width, color channels in the range 0 to 255, which is what our values are up here. They're from 0 to 255, red, green, and blue, to a torch float tensor of shape, color channels, height, width in the range 0 to 1. So it will take our tensor values here, or our NumPy array values, from 0 to 255 and convert them into a torch tensor in the range 0 to 1. We're going to see this later on in action, but this is our first transform. So we can pass data through that. In fact, I'd encourage you to try that out. See what happens when you pass in data transform. What happens when you pass it in our image as array? Image as array. Let's see what happens, hey? Oh, image should be PIL image. Got class image as array. Let's see what happens, hey? Oh, image should be PIL image. Got class NumPy array. What if we just pass in our straight up image? So this is a PIL image. There we go. Beautiful. As array. Let's see what happens, hey? Oh, image should... There we go. Beautiful. So if we look at the shape of this, what do we get? 3, 64, 64. There's 64. And what if we wanted to change this to 224, which is another common value for computer vision models? 224, 224. You see how powerful this is, this little transforms module, the Torch Vision library? We'll change that back to 64, 64. And then if we have a look at what D type of our transform tensor is, we get Torch Float 32. Beautiful. So now we've got a way to transform our images into tensors. And so, but we're still only doing this with one image. How about we progress towards doing it for every image in our data folder here? But before we do that, I'd like to visualize what this looks like. So in the next video, let's write some code to visualize what it looks like to transform multiple images at a time. And I think it'd be a good idea to compare the transform that we're doing to the original.
Residents here winter upstairs and move down to the cooler courtyard level in the summer.
These orange trees are great for shade. They never lose their leaves.
And refreshing too on a hot day.
Well, not to eat. These are sour orange trees. We just use them for vitamins, perfume, or that kind of marmalade the British like.
Oh, that bitter English marmalade, yeah.
It's made with our oranges.
The Santa Cruz neighborhood comes with a timeless beauty. Savor the simple elegance of Sevilla. The delicate charms of Santa Cruz are just a few steps from Sevilla's immense cathedral. It's the third largest church in Europe after St. Peter's in the Vatican and St. Paul's in London, and the largest Gothic church anywhere. When they ripped down the mosque that stood on this site in 1401, the Reconquista Christians bragged, "We'll build a cathedral so huge that anyone who sees it will take us for madmen." You could fit a soccer field in here. Everything is supersized. The towering main altarpiece is covered in gold leaf. Constructed in the 1480s, it's composed of hundreds of figures. It tells the story of the life of Jesus in 40 scenes from his birth to his resurrection. The choir, an enclosure within the cathedral for more intimate services, surrounds a spinnable music rack. It held giant hymnals, large enough for all to chant from in an age when there weren't enough for everyone. In the transept, 4 pallbearers carry the tomb of Christopher Columbus. They represent the 4 medieval kingdoms that became Spain: Aragon, Navarra, Castile, and Leon, each identified by their team shirts.
Columbus even traveled a lot after he died. He was buried first in Sevilla, then moved to Santo Domingo, then to Cuba, and after Cuba earned its independence from Spain around 1900, he sailed all the way back here to Sevilla. Is he really in there? Sevillanas like to think so.
All that survives of Moorish Sevilla's main mosque is its courtyard of orange trees and a towering minaret. The tower offers a brief recap of the city's history, sitting on a Roman foundation, a long Moorish period, capped by the Christian age. The Moors built its spiraling ramp to accommodate a rider on horseback. Somebody climbed this tower 5 times a day to call Sevilla's Muslims to prayer. Today, tourists gallop up for fine city views. And the former minaret functions as the cathedral's bell tower. It's topped with a bronze weather vane, a statue that symbolizes the triumph of faith. Perhaps the most famous of religious icons in this very religious city, the Virgin of the Macarena, can be found in the nearby Basilica de la Macarena. Grab a pew and study the Weeping Virgin. She's a 17th century doll, complete with articulated arms and human hair. She's even dressed with underclothes. With crystal teardrops, her beautiful expression, somewhere between ecstasy and sorrow, touches pilgrims.
Sevilla's Semana Santa, or Holy Week celebrations, are the most magnificent in Spain. During the week leading up to Easter, the city is packed with pilgrims, witnessing grand processions carrying elaborate floats through the streets.
The 2 most impressive floats of the festivities are parked behind the altar. The biggest float, slathered in gold leaf, shows the sentencing of Christ. Pontius Pilate is about to wash his hands. His wife cries as a man reads the death sentence.
While pious Sevillan women wail in the streets, relays of 48 men carry this 3-ton float on the backs of their necks. Only their feet show from under these drapes as they shuffle through the streets from about midnight until 2 in the afternoon each Good Friday.
This float, with the Weeping Virgin from the church's altar placed regally in the center, is the hit of the parade. It's festooned with wax flowers and candelabra. It seems fragile, all silver and candles. Locals explain it's strong enough to support the roof, while delicate enough to quiver in the soft night breeze.
Have you actually seen this one going through the streets?
The queen of the city, you mean?
Yes.
Of course. She even wears her crown, and that day she looks absolutely beautiful. When she goes through the streets, people get crazy. They can't explain all those emotions, and they clap, or they cry, or they throw petals from balconies.
What's so special about this particular Mary?
She knows everything about us, because we have been telling her our problems for centuries. Her name is Hope, which is what we all need.
With all this religiosity, it's no surprise that Sevilla is also famous for letting loose in vibrant festivals.